Okay. Okay. So the symplectic form is a two form. It's defined in the same way that we did for R2N. It is just omega theta of xi comma eta is the Sasaki inner product of j theta xi with eta. Okay. So note that j theta, this is clearly an isometry for the Sasaki metric, right?
Yes. Sir, usually a linear map which whose square is minus of the identity on a vector space is called a complex structure or something. Why are we using almost complex structure?
That's a good question. Let me explain. 1 second. So I'll tell you why. So first of all, this j theta is an isometry for Sasaki metric. Okay, for Sasaki. Inner product. Yeah, okay, before I move on. So you're right. Normally, if I have a endomorphism of a vector space, a finite dimensional vector space, and I have an endomorphism J whose square is minus identity, then that is called a complex structure on the vector space V, because I can use J to give my real vector space V the structure of a complex vector space. Basically, I have to define multiplication by complex scalars. I already know how to multiply by real scalars. I just need to tell you what is multiplication by I, and you define I dot V to be JV for any vector V in V, right? So multiplication by I is played by J. The role of multiplication by I is played by J, and then this becomes a complex vector space, okay? So, right, so an endomorphism J whose square is minus identity is called a complex structure on a single vector space. Now suppose I have a manifold, and on each tangent space I have an endomorphism whose square is minus identity, okay? Then each tangent space becomes a complex vector space, right? But then there is a question that is the manifold actually a complex manifold? In other words, do I have charts into Cn so that the change of charts is biholomorphic? And, or rather, well, do I have charts into Cn so that under these charts, my isomorphism on the tangent space, so my charts will identify the tangent spaces with Cn, right? So the question is, under this identification of the tangent space with Cn using the charts, does the endomorphism J get identified with multiplication by I from Cn to Cn? So the question is, can I find such charts? So you're given J from each tangent space Tpn to Tpn. Can I find locally charts Z1 to Zn, mapping an open set U in N to Cn near any point, so that the derivative of the chart conjugates the endomorphism J on Tpn to the endomorphism multiplication by I on Cn. All right. So this turns out to be a very difficult to solve system of partial differential equations, and it's a very famous theorem of Nirenberg, Louis Nirenberg, who worked in PDEs, and who was awarded the Abel Prize for this towards the end of his life. And also maybe the Fields Medal, if I'm not wrong. I don't remember. But anyway, he proved a very major theorem that we'll say that an almost complex structure, that means an endomorphism of the tangent bundle whose square is minus identity. This is integrable if and only if a certain tensor called the Nienhaus tensor vanishes. So that is some differential condition. Okay. So some differential condition, if it is true, it's a necessary condition for integrability. He showed that it is also sufficient. He showed it is also sufficient. And that's a major piece of real analysis. Okay, it's a major result in real analysis and PDEs. Okay, so this is actually a very deep question, that when is an almost complex structure integrable? Does it make sense, Utshap?
Yes, sir, yes.
Okay, okay. So you can look up Nirenberg and you'll find, some writing up about this. It's a very famous problem, this integrability of almost complex structures. So that's why they're called almost complex, right? There are manifolds where you have an almost complex structure, but it's not coming from a complex structure, where complex structure means charts into Cn so that the changes of charts are biholomorphic. In other words, the manifold becomes a complex manifold, right? The manifold becomes a complex manifold.
Right, sir, right.
Do you understand? So not every almost complex structure is integrable. You may not be able to integrate to find charts where the endomorphism becomes multiplication by I. All right.
Okay, sir.
Yeah, so that's okay. So for us, we don't care about whether it's integrable or not. We just can use it to define a symplectic form. So define omega theta, a two form from T theta Tn cross T theta Tn to R bilinear form by omega theta of xi eta is defined to be Sasaki inner product of j theta xi eta. Is this clear? Okay. Then,
yes,
as before, for the example of Cn or R2n, omega theta is alternating. So that's because J is an isometry for the Sasaki inner product and J squared is minus identity. That will tell you that omega is alternating. And also because J is an isomorphism, that will tell you that, so that will tell you that omega is non-degenerate, right? Yes?
Yes.
Right, sir.
Okay. So explicitly, what is this? Explicitly, this will be what? J theta xi is minus xi v xi h, inner product with eta h eta v. So this will be minus the inner product of so xi v with eta h. So xi v is k theta xi and eta h is d pi theta eta plus inner product of xi h with eta v, right? So xi h is d pi theta xi, and eta v is k theta eta. Is this clear? Yes?
Yes.
Okay. So to finish, the last thing we'll show. So what we haven't shown yet, we'll show later that omega is closed. So we'll show this in the next class. So we need to show that omega is a closed two form, right? We've shown that it's symplectic, meaning non-degenerate on each tangent space to Tm. So we'll show later that omega is closed. In fact, omega will be exact. So therefore it will be closed. Okay, we will in fact find a one form omega alpha such that omega is d alpha. So in fact, omega is exact. In fact, omega will be exact. So to finish, let me just finish by saying that the geodesic flow on the tangent bundle, we can easily show is a Hamiltonian flow. And what is the Hamiltonian function for the geodesic flow? It's what's called the energy function, which is just the norm squared of a vector. Okay, so points of Tm are pairs x comma v. My function h on Tm is half norm squared of v. All right. So this is called the energy function of M. Then the Hamiltonian vector field of H is the geodesic vector field G. Okay, so in other words, dH at theta of xi is equal to omega theta of g theta xi for all xi in t theta Tm and theta in Tm. Is this clear? The statement? Okay. Yes? Are you there?
Yes, sir.
Yes, sir.
Is the statement clear? The Hamiltonian vector field of this energy function is the geodesic vector field. Okay. The Hamiltonian vector field of this energy function is the geodesic vector field. That's the vector field generating the geodesic flow, right? Okay.
Okay.
Yeah, so let's prove this. It's a very short proof. So you're given a tangent vector xi in t theta Tm, and theta is a point x comma v in Tm. So you let z be a curve in Tm so that z0 is theta and z prime 0 is xi, right? So z of t I can write as a curve alpha in M together with a vector field capital Z along alpha, right? So I can write it as a pair alpha t comma zt. Okay. Now what is dh theta of xi? This is ddt at t equal to 0 of h of zt, right? And h of zt is just the norm squared. So it's the norm squared of this capital zt. So this is ddt at t equal to 0 of half capital zt, capital zt. So by compatibility with the metric, this is inner product of dz dt 0 with z0, right? Yes?
Yes.
Yes, sir. Yes.
And what is dz dt at 0? By definition, this is k theta of xi, right? This is the definition of the connection map. So this is k theta of xi, and z0 is v, right? So this is inner product of k theta xi with v, right? Yes?
Yes, sir.
Yes, sir. Yes, yes.
And now what is omega theta of g theta xi? So if I write it in terms of horizontal and vertical components, g theta, remember we saw was v comma 0, right? Yes, g theta was v comma 0.
Yes.
Horizontal component was v and vertical component was 0. And xi, the components are d pi theta xi, k theta xi. So this omega applied to this will be what? I have to take j of this and then Sasaki inner product. So j of this will be 0 comma v, And then when I take Sasaki inner product, I'll get 0 inner product with d pi theta xi, that will vanish, and V inner product with k theta xi, right? So I get k theta xi V. Is that clear?
Yes, sir. Yes.
Okay, so therefore, this geodesic vector field is the Hamiltonian vector field of the energy function. Okay. So this energy function you think of as kinetic energy, right? This is the V is the velocity vector. This is the norm squared of the velocity. So it's half. So if the mass is 1, this is half mv squared, right? This is kinetic energy. And the geodesic flow is the Hamiltonian flow of the kinetic energy. Does it make sense?
Yes, sir.
Yes, sir. Yeah.
Okay, so the geodesic flow, it will preserve the level, it will preserve H, right? So the norm squared is preserved, that we know. The norm squared of the tangent vector gamma prime is preserved, right? For a geodesic has constant speed. So that we already know that geodesics preserves, they have constant speed. So that means this H function is preserved. But more than that, it preserves the volume, right? So it preserves the volume on the tangent bundle. So the geodesic flow will be volume preserving. And also it will preserve level sets of H. So if M is a compact manifold, then the level sets of H will be compact, right? Let's say that when H is equal to 2, H is equal to half, that is the unit tangent bundle, right? That means the set of unit tangent vectors. So that is a compact manifold when M is compact. The unit tangent bundle is a compact manifold, and the geodesic flow will preserve this compact manifold. It's a submanifold of the full tangent bundle. And so therefore you will have a recurrence for the geodesic flow. You will have recurrence for the geodesic flow. Okay, because the volume measure on Tm will induce a measure on T1m on the unit tangent bundle. And so this will become a volume preserving flow on a compact manifold, the unit tangent bundle. And therefore, almost all orbits of the geodesic flow will be recurrent. So geodesics will move around and come back close to where they started for almost every starting tangent velocity vector.
And this is the analog for Lewis theorem.
Well, yeah, I mean, it's using Liouville's theorem, right? It's using Liouville's theorem. So that the symplectic form is invariant. So the symplectic form will be invariant under the geodesic flow. It will be invariant under the geodesic flow. And so the symplectic volume, it's easy to see is the same as the volume of the Sasaki metric, the volume form of the Sasaki metric, because, well, it's n factorial times the volume form of the Sasaki metric, because, so if I take, E1 to En, let's say an orthonormal basis of H theta, subset of T theta Tn, and I take Fi to be J theta of Ei. So then F1 to Fn, this will be an orthonormal basis of the vertical subspace V theta, right? Yes?
Yes.
And together E1 to En, F1 to Fn, this will be an orthonormal basis of T theta Tm and omega theta will be summation over I, EI star wedge FI star, right? Yes? Because this is just what I did in CN. It's the same thing I'm doing in this 2n
Yes, sir.
vector space, right? So omega theta will be this, and omega theta power n will be n factorial E1 star wedge F1 star wedge En star wedge Fn star, and this thing E1 star wedge F1 star up to En star wedge Fn star, this is equal to the Riemannian volume element, right?
Yes, sir.
Because how is the Riemannian volume form defined? It is the unique top dimensional form whose value on any orthonormal basis is 1, right? So this is 1 on the orthonormal basis, E1, F1, E2, F2 up to En F1, En Fn, right? So this is the Riemannian volume form of the Sasaki metric. Is this clear?
Yes, sir.
Okay, so if I look at the tangent bundle as a Riemannian manifold with the Sasaki metric, so then it has a Riemannian volume form, and the symplectic form power n is just n factorial times the volume form, and the symplectic form power n is invariant under the geodesic flow. So this tells you that the geodesic flow preserves the Sasaki volume, right? It preserves Sasaki volume in the tangent bundle. Okay. All right, so let's stop here. Any questions? Any questions? Okay, so if there are no questions, let's stop then, and I'll see you on Thursday.